Okay guys, so this is actually going to be the last section that we cover, and I hate that for you all, because we could have gotten into a lot more had we been actually in school, but due to the circumstances, this will probably be the last section that we do. No, Campbell. So this one is the derivative in the tangent line problem. We have talked about this multiple times, the derivative in the tangent line. And it says to recall the summary at the end of the lesson on an introduction to derivatives, where we said that the rate of change of a linear function is given as the slope of its graph. If the graph is a curve, we can approximate the rate of change or slope at a single point P by choosing another point Q extremely close to P on the curve. And then we can find the slope of that line between the 2 points. So if you choose 2 points that are extremely close together, your approximation will be as close to the exact value of the slope as you want or need. And we call this instantaneous rate of change at P, or the derivative. So if you remember, those are the same things. So example 1, when you join 2 points on a curve, you're drawing a secant line to the curve. If you move point Q closer to point P until the 2 points coincide, then you have drawn a line that is tangent to the curve, which is our tangent line. So this first one, if you connect those two dots, that gives you a secant line. Move it a little closer, that's still a secant line, it's still 2 points. And then move Q to where it is P, and we just have 1 point. That's our tangent line. So example 2, it says, let's explore what's happening algebraically. That is delta x, delta x, or the change in x, is becoming infinitely smaller as Q approaches P. And we want to calculate the slope of the secant line PQ using the coordinates P is a f of a and Q is x f of x. So this is going to look confusing and stuff, but it's just the change in y over the change in x. The way they have it written, because we don't have certain points, it's written like this, where f of x plus delta x is point P. So it's like the y value of P minus the y value of Q all over the y value, the x value of P minus the x value of Q. So, and then that's just it simplified. This is just a regular formula, but we won't really be using that. They're just showing you the generic or the general form. Mama. You can probably hear Campbell yelling. So as Q approaches P, delta x is approaching 0, and this is the limit problem. And the slope of the tangent line is the limit of the slopes of the secant lines. So we've already talked about this, and you'll probably remember it quite well, actually. F prime of x is actually the limit as h approaches 0 of f of x plus h minus f of x all over h. So we've done this multiple times before, which is a good thing. You'll actually know it. So graphically, it says the derivative of a function at point P is the slope of a tangent line to the graph of f of x at P. And numerically, that just means that the derivative at a point is the limit of slopes of the secant lines, or the limit of the difference quotient. The definition of a derivative, it says the derivative of a function f with respect to x is the function f prime, which is the derivative. So f prime of x, that's the limit as h approaches 0 of f of x plus h minus f of x all over h. So the derivative is this limit. And it says provided the limit exists. And it gives us a note here that the domain of f prime, which consists of all values of x in the domain of f of x, for which the limit exists, may be smaller than the domain of f. If f prime exists, we say that f is differentiable at x. Okay, using limit notation. It says there are many ways to denote the derivative of a function y equals f of x. Some of the more common notations we will use are shown below. So this is like how derivatives are denoted. So we can say f prime of x, that's this top one. We can say y prime, because remember y and f of x are the same things. We can say dy over dx, or some people just say dy dx, or the derivative of y with respect to x. That's going to be the same as if we were to say this next one, df dx. It's the same thing like up here where f and y are kind of interchangeable. It's the same here. And then you have d dx of f at x, or f of x, however you want to say that. But you'll see it written one of these 5 ways. Okay, alternate forms of the derivative. It says the derivative at a point x equals a is also found by f prime of a being equal to the slope of the tangent line, which we know. Remember, if we find this derivative, that's our slope. And then that's also equal to the limit as h approaches 0 of f of a plus h minus f of a over h. We've talked about that one. Or we use this one whenever, remember, we have an actual point value that we're evaluating. So if we have like 2, we would plug 2 into this second limit. Okay. So example 3 says, to use the limit process of the derivative to find the general formula for the derivative of f of x equals 2x squared minus 3x. So it wants us to use the limit process, and since we don't have an actual point value to use, we're going to use the one that has the h in it. So f prime of x equals the limit as h approaches 0, and remember, anywhere we see an x up here, we plug in x plus h. So we have 2 times x plus h squared, that's that part, minus 3 times x plus h, and then remember in the formula it's minus f of x, so we subtract this original function. And all of that is over h. So if we expand this x plus h squared and multiply everything by 2, we're going to get 2x squared plus 4xh plus 2h squared. This middle part gives us minus 3x minus 3h, and then minus 2x squared plus 3x. And that's still all over h. And so you can see we can mark a couple things out. And so that leaves us with 4xh plus 2h squared minus 3h all over h. So remember, this is where we start to factor out the h on the top. And that's what we're left with, all over h. So we can mark those out. And we're left with this, 4x plus 2h minus 3. And for that last step, that's when we plug in 0 for h, and we'll get 4x minus 3 is our either tangent line or derivative. All right. When I say tangent line, I mean the slope of the tangent line. I don't just mean that's the equation of the line. All right, example 4. Use the alternate form of the derivative to find f prime of a. So this is the one that we just looked at earlier on this page, because we have an exact point. So we're going to use the f prime of a is the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so we have the limit as t approaches 1, because we're using t's and this is 1. So the limit as t approaches 1, okay, and it's f of x, so that's square root of 3t plus 1, minus f of a, so that's going to be negative 2. So if we were to plug 1 in for this function, we'd have 3 times 1 plus 1, which would be the square root of 4, which is 2. So that's how we get this value here. And all of that is over x minus a, so x minus 1, or t minus 1. Okay, we have a square root, so we have to rationalize. So we're multiplying numerator and denominator by the square root of 3t plus 1 plus 2. Hopefully you guys remember that. Okay, the square root of 3t plus 1 times the square root of 3t plus 1 is just 3t plus 1. Negative 2 times 2 is negative 4. Okay, and that is over. We'll just write this as one big thing down here. So 3t plus 1 minus 4, that's going to give us 3t minus 3. And so we can factor out a 3 from that and get t minus 1. And then we still have this on the bottom, so we can mark out our t minus 1s. And that just gives us 3 over the square root of 3t plus 1 plus 2. Now we can just plug in that 1 right here, because it's simplified. So if we plug in a 1, we get 3 over the square root of 3 times 1 plus 2, which gives us this 3 over 4. Alright, last page. And I don't know if I'll run out of time in this one or not. So example 5, for the function f of x, find a general formula for the slope of the tangent line at any point on the curve. So it says at any point on the curve we're going to find a tangent line. And then once we find that tangent line, we're going to find the slope of it at x equals 2 and x equals 0. So we're going to use the one that has h in it because we don't have a specific point. We want to use whatever we get here for 2 different points. So we have the limit as h approaches 0 of x plus h squared minus 3. I don't know. Campbell hit Siri. Okay. Minus f of x. So minus our original function all over h. Alright, so we have, if we expand that binomial, we get this. Minus our middle term, which is minus 3x plus, or minus 3h plus 2, and then change the sign of everything in this last set of parentheses to give us this. And we'll mark stuff out, and that's all over h. Okay, so this is what's left, minus 3h over here, and we'll factor out an h, and that gives us 2x plus h minus 3. Mark out those h's and plug in a 0 for h. We get 2x minus 3 as our function, or our general formula for the slope of the tangent line. Okay, now we want to use that general formula, this one right here that we just found, and plug in 2 and then plug in 0. So when it's 2, we get f prime of 2 is 1. And when it's 0, we get negative 3. So those are your answers for this. Okay, the last part, I have 2 minutes to get through this. I think we can do it before the video cuts off. Okay, so example 6, use the limit definition to compute f prime of a and find an equation of the tangent line for f of x equals 1 over x plus 3 at a equals negative 2. So we do have a value here, and we can use that first, or the alternate formula, the one that we used on example 4, the f of x minus f of a. So we have the limit as x approaches negative 2 of f of x minus f of a. So we're going to plug negative 2 in for that equation up here. And that's going to give us 1. So it's going to be minus 1. And that's all over x minus a. So x plus 2. X minus a negative 2 is x plus 2. Alright, so we want to have an LCD up here, which is going to be x plus 3. So to do that, they get this. So find your LCD, you should get this. Okay? And it's still over x plus 2. Alright, so now, if we do this, we want to combine like terms. And it's still over x plus 3. And this part right here is going to equal negative x minus 2. So I went ahead and put that out here because what we're going to do is we're going to keep change flip. So it's going to be negative. And actually, we can factor out a negative from both of those things. And it'll be negative x plus 2 over x plus 3. And if we keep this, change this to multiplication, and flip the bottom to 1 over x plus 2, then the x plus 2's will go away. So if you want to write it out a little longer, you can. I'm running out of time. Okay, so we get this. plug in and we get a -1. So our point is -2, -1. Oh my goodness, I'm running out of time. That's our point. We know our slope is, oh no. Okay, find the tangent line.